Hi everyone, welcome back to 340. My name is Dr. Free and we will be starting with our traditional recap. Alright, so starting off here, remember we were in the middle of derivation when we started last class. This is the point that we were at, and we were about to arrive at a glorious solution. So if we continue down to this next line here, the solution for this involves u, mu, this constant we discussed earlier, as well as this c term that we don't know yet. So moving onwards, we're going to take a look at the initial conditions. You there in the blue jacket? What's on your phone?
I don't know, text messages.
Alright, to determine what that c value is, for the first initial condition we're going to look at is, of course, when theta is equal to theta naught, as that is obviously a good choice for determining that. And then going in throughout that, we look at the values for these three different differentials, end up getting them all equal to 0, which is so nice. And then along with plugging in values from the last lecture, again, the derivation that's been going on a couple lectures now, we start getting into specific energy then to finalize that constant right there. And with that, we're going to get some class participation. All right, would you like to come up here? All right, awesome. Be sure to say your name.
All right, my name is Carmen, and so we're going to plug everything back into energy equation up here, and then we're going to end up with the constant C in the term as well. Since we know the specific energy, then we were able to solve for the C constant. We're just going to plug everything back into the velocity equation. We got R equals to h squared plus over mu over everything that we got from the previous equation, which is 1 plus square root of 1 plus 2 specific energy h squared over mu squared cosine theta. Finally, what we got is the Koenig equation.
All right, now that we've come to our solution, do we feel the ultimate happiness?
All right, so my name is Will. You're finally going to be able to take this really long derivation and apply it to something in real life, and the conic solutions of the different types of orbits depending on the energy that we have. So we have three different potential conic solutions. The first is when the eccentricity is 0. And when the eccentricity is 0, that means that we are in a circular orbit where the periapsis and the apoapsis are the same. And then we have elliptic orbits if the energy is in between 0 and 1, where we then have a periapse of the semilattice rectum, which is indicated here by P, over 1 plus the eccentricity, and the apoapsis is the same thing, except in the denominator we have 1 minus E. And the next time, which is today, we are going to look at hyperbolic orbits.